In this lesson, we're going to take a look at some more angle identities. Now, at this point, should have been already introduced to some of the basics, our rational identities, our reciprocal identities, and our Pythagorean identities. Well, through this lesson, we're going to take a look at several more sets, and we're going to begin this study with a look at what are called odd and even functions. Now, perhaps at this time in Algebra2 studies, you've already run across this concept of odd and even functions, but just in case you haven't, here's how we define them. An odd function would be any function where f of the opposite of x equals the opposite of f of x. Now that's very much algebra speak, so let's take a look what that would look like. If I have a graph on a standard set of axes, if I have a point here, so this is x, and this is f of x. What this is saying is that if I put in the opposite x value, so I go the same distance, other direction on x, I'm going to end up with the same value, opposite direction for y. And what that would look like is a graph that is point symmetric about the origin. So our x cubed function is this, our basic linear function, and several of our trig functions come out in here also. In fact, specifically, we get the trig functions of tangent of x and also sine of x. If we take a look at these, and one thing I do is graph it on a graphing calculator, if I can turn the calculator upside down and the graph appears exactly the same, then I'm looking at an odd function. Okay. Now for even functions, we would be looking at f of the opposite of x equals just f of x. So again, graphically, I have my axes set up, and if I put in a value for x and get out a particular f of x, if I put in the opposite value of x, I'm going to get out the exact same value for f of x. So anything that has a line symmetry about the y-axis, such as y equals x squared, we'd be looking at being an even function. Or, in terms of our trigonometry, cosine of x is an even function. So these angles, or these identities, are referred to as our negative angle identities. If I put in the negative value for the same angle, what do I get out? Do I get out the same response, or do I get out the opposite? Now here, did work them through for tangent, sine, and cosine. The question would come, do they apply also to their reciprocal identities? Does cotangent fall here? Does cosecant fall here? And does secant fall here? If you picture their graphs, yes, they do have those same characteristics. So these work for our three basics as well as their corresponding reciprocal identities. Next set that we're going to take a look at here are cofunction identities. And what those say, and this goes back to an earlier study when we were looking at the phase shifts and functions of sine, cosine, and tangent. Sine and cosine were a simple phase shift off of each other, while all of our co-functions work this way. Specifically, we have that the sine of pi halves minus theta is cosine theta. Of course, we can do this for the equivalent in degrees. So the sine of 90 degrees minus whatever our angle theta is going to be cosine of theta. Then our cosine of pi halves minus theta is sine of theta. And these ones are very popular to be showing up in things such as standardized tests. There's typically a question or several questions a year in regards to a triangle is provided. They give you a value of the sine of one of the angles, and they ask you what the cosine of 90 minus that unknown angle is. And it's simply the same thing. So the third one that we typically look at is that the tangent of pi halves minus theta is cotangent of theta. Now again, we're looking at these from our typical trig ratios that we discussed, but they are also true about their reciprocal identities. So for cosecant, secant, and cotangent, these would work back the same way. So what are some other identities we're going to come across now? We have our odd and even, or our negative angle identities. We have our cofunction identities. And we also have our angle differences and angle sum identities. So let's start out with the sine of a minus b. Well, this will work itself out as sine of a times the cosine of b minus the cosine of a times the sine of b. So if I'm trying to find a specific value that isn't one of the items on our unit circle, if I can subtract them in some way in order to create that from items known on my unit circle, then I can apply this identity. We also have similar ones for our cosine and tangent, and they look as such, where we have the cosine of a minus b is cosine of a times cosine of b plus sine of a times sine of b, and the tangent of a minus b is tangent of a minus tangent of b divided by 1 plus tangent of a times tangent of b. So if we know our unit circle well and we're able to move in certain values that we are aware of, we can apply these differences to arrive at some others. For instance, if I needed to know something specific about, let's say 15 degrees, well, I can simply say that that is 45 degrees minus 30 degrees. So if I need to find, say, the tangent of 15 degrees, I can simply say that A is my 45, B is my 30, and then apply my appropriate A's and B's into these formulas. Now, we do have our angle differences. Then, using our negative angle identities, our odds and evens, we can also come up with angle sums. Because what happens if it's plus B inside of here? What happens to all these items? Well, what is the sine of a negative angle? What's going to happen there? What's going to happen here? What's going to happen to the tangents of these b portions when we do it? Cosine, it makes no difference. Sine and tangent, it does, because they're odd functions. So what we end up with is stuff that looks like this, where we end up with the sine of a plus b is sine a cosine b plus cosine a sine b. The cosine of a plus b is cosine a cosine b minus sine a sine b. And the tangent of a plus b is tangent a plus tangent b divided by 1 minus tangent a tangent b. So you can see that on our sine and tangent identities, all the signs changed. On our cosine, it also changed, but simply because it's affecting that sine portion of it. Okay, so how can we apply some of these identities to find new values or to verify other things? Well, we're going to compute the exact values of these following expressions. So first up is the cosine of 15 degrees. So I'm going to pull up what I know. That cosine of 15, that could be written as the cosine of 45 minus 30. So applying my formula, I get cosine 45 cosine 30 plus sine 45 sine 30. Running a little bit over here. So what are these exact values from our unit circle? Cosine of 45 degrees is square root of 2 over 2. Go multiply that by the cosine of 30, which is square root of 3 over 2. To that we will add sine of 45, which is also root 2 over 2, and sine of 30, which is 1/2. So applying all the algebra and mathematical pieces that we have our square root of 6 over 4 plus square root of 2 over 4. Nicely, we have common denominators. So we end up with an exact value of square root of 6 plus square root of 2, all divided by 4. And there we have the exact value of the cosine of 15 degrees. What if we were to take a look at our sine of 105? So I'm going to drop a quick line here, separate out my items, and then let's take a look at our next one. So sine of 105, I'll start up here. We're going to write that as the sine of, good way to make 105 is I can say, well, this is 60 plus 45. Okay, so applying in our formula, we're going to end up with the sine of 60, the cosine of 45, minus the cosine of 60 and the sine of 45. Okay, so sine of 60 is square root of 3 over 2. Cosine of 45 is square root of 2 over 2. From that, we're going to subtract 1/2 cosine of 60, and then sine of 45, again, our root 2 over 2. So what we end up with is square root of 6 over 4 minus square root of 2 over 4, which is simply square root of 6 minus square root of 2, all divided by 4. Now, I don't know where you might be in your learning of trigonometry, but if you have not learned or memorized the unit circle, you might be seeing here that having these values memorized is coming in quite handy. So do take the time to learn that unit circle because it's going to be of great benefit going forward. So anything that we can use our basic pieces off of our unit circle in order to create, we can either add or subtract those values in order to come up with exact items. Now, yes, I could put this into my calculator. There are a few rare calculators in existence that will give you an answer such as this. Most will shoot out decimal approximations. I don't really want my decimal approximations. I want exact answers only. Okay. What about verifying an identity? So we want to verify the coangle identity for sine to cosine functions. In other words, if I start out with sine of pi over 2 minus x, how can I show that that is the cosine of x? Okay, so for this one, we start out with our, if you notice it, this is a subtraction or an angle difference identity. So this would be the sine of pi halves times the cosine of x minus the cosine of pi halves times the sine of x. This is all working my left-hand side only. So what is the sine of pi halves? That is 1. Cosine of x is just going to be cosine of x. Minus cosine of pi halves is 0 times the sine of x, which is just sine x. Of course, anything times 0 is 0, so all we're left with is cosine of x. So these functions and identities start becoming a little bit interdependent. I can go through and derive my sum or difference identities using previous ones, but I can also use the sum or difference identities in order to prove my coangle identities. So just becoming familiar with them, knowing what's out there and available, will allow us to be able to show certain relationships or come up with more specific items in order to be able to use exact values rather than decimal approximates. The further we get in math, the more we're going to want to have those exact values, and the less helpful decimal approximations can be. So we now have 6 different categories of angle identities between just our basic, reciprocal, rational, Pythagorean, and now our negative angle, coangle, sum, and difference. You can lump sum and difference together. That would give us 6 categories. If you want to separate them out, it gives us 7. So in a typical study of trigonometric relationships and identities, we should have 2 more sets to go, and those would be half angle and double angle, and those ones will be coming up at another time in another lesson.